Hello everyone, my name is Wang Jiayi, and today I'm going to present a fundamental concept in mathematical analysis. It's the uniqueness of the limit of a sequence. This is one of the first things we learned in our course, and it's a cornerstone for everything that follows in calculus. In this presentation, I will start with a formal theorem, explain why it matters in the real world, give you some geometric intuition, work through the formal proof, and then I will explain the theorem from a topological perspective and give a short conclusion. Now let's start with the theorem itself. It states very simply, a sequence cannot converge to two different numbers. In other words, if a sequence is going to settle down, it has to settle down at one specific spot. We need this for the logic of calculus to stay consistent. Now let's talk about why this theorem is so important. First is physics and real-world logic. Think about an object's velocity. It is impossible for a particle to have two different speeds and at the same moment. Limits are used to describe physical quantities, so they must behave in a realistic way. If limits were not unique, physical models would become meaningless. Second is the algebra of limits. Many limit rules depend on uniqueness. For example, if the limit of an is a and the limit of bn is b, then the limit of an plus bn is a plus b. If a or b were not unique, then this rule would not make sense anymore. Thirdly is the Cauchy criterion. The Cauchy criterion says that the terms of a convergent sequence must get closer and closer to each other. If a sequence could go to two different places, the terms wouldn't be able to cluster close together, which would break the rules for convergent sequence. To understand the uniqueness of limits intuitively, let's use a real-world analogy involving the Malaysia railway system. Imagine a train traveling on a track. It is physically impossible for that train to arrive at Kuala Lumpur and Penang at the exact same time because these two cities are hundreds of kilometers apart. In mathematical analysis, closeness follows a similar logic. If we say a sequence is getting infinitely close to a limit L1, it eventually becomes trapped near that value because L1 and L2 are separated by a fixed distance. Being close to one automatically means the sequence must be far from the other. The geographical separation is the heart of our proof. Now, let's translate this intuition into our formal language of analysis. Mathematically, we describe these areas of closeness using neighborhoods, which we can visualize as bubbles. We start by assuming that there are two distinct points L1 and L2 on the real number line because they are not the same. So there is a fixed positive distance between them, which we call d. Now, here is the most important part of the proof. We draw a protective bubble around each point. We specifically choose a radius called epsilon that is less than half of the distance between L1 and L2. By making the bubbles this small, we guarantee that they are disjoint, meaning they never ever overlap or never touch each other. This is possible because the real numbers have the Hausdorff property, allowing us to always separate distinct points with these neighborhoods. Next, we consider our sequence Xn. If the sequence converges to L1, the definition of convergence tells us that the tail of the sequence, the infinite number of terms at the end, must eventually enter L1's bubbles and stay there forever. Here is a contradiction. If the tail of our sequence is already trapped inside the bubble of L1, it is physically and logically impossible for those same terms to be inside the bubble of L2 at the same time. Since the sequence cannot be in two disjoint places at once, so the limit must be unique. Now let's dive into the formal proof using proof by contradiction. First, we assume the opposite of what we want to prove. Suppose that our sequence xn actually converges to two different limits L1 and L2, where L1 is not equal to L2. Because these 2 points are distant, the distance between them must be positive. To create our protective bubbles, we define epsilon as exactly half of the distance. This choice is crucial because it ensures that the neighborhoods around L1 and L2 will never overlap or touch. Next, we apply the formal definition of coverages to both limits. Since the sequence coverages to L1, there must be a starting point N1, such that all terms after N1 stay within epsilon of L1. Similarly, because it also coverages to L2, there is another point N2, after which all terms are within epsilon of L2. Now here is a key move. We let n be the maximum of n1 and n2. By picking the larger number, we guarantee that for any n greater than n, both conditions are true at the same time. The sequence terms are now trapped in both neighborhoods simultaneously. Finally, we look for the contradiction using triangle inequality. We start by looking at the total distance between our two assumed limits L1 minus L2. Inside the absolute value, we add an abstract xn. This doesn't change the value, but it allows us to split the distance. According to the triangle inequality, this distance is less than or equal to the sum of these two parts. The distance from L1 to xn plus the distance from xn to L2. From our previous step, we know both these parts are smaller than epsilon. So the absolute value of L1 minus L2 must be strictly less than epsilon plus epsilon, which is 2 epsilon. But wait, remember how we define epsilon? We said 2 epsilon is exactly equal to the absolute value of L1 minus L2. This leads us to a ridiculous conclusion. The distance is strictly less than itself. This is clear contradiction. A number cannot be smaller than itself. Therefore, our initial assumption must be false. L1 must equal to L2, providing that the limit of a convergent sequence is indeed unique. Now let's look at why this proof actually works from a deeper perspective. We rely on two important features of the real numbers. First is the Hausdorff property. In simple terms, this means that for any two different points, we can always find two separate bubbles that do not touch each other. In our proof, this property is what allowed us to choose a small epsilon to separate L1 and L2. Because our bubbles never overlap, the sequence cannot stay in both at the same time. Secondly is the real numbers from metric space. This just means we have a precise way to measure distance using absolute values. This ruler allows us to use the triangle inequality to show exactly how close the terms are to the limits. So the uniqueness of a limit isn't an accident, it's built into the very structure of our number system. To end my presentation, let's look at what we have learned today. First is intuition. Just like a train cannot be in two different cities at the same time, the end of a sequence cannot be in two separate places. Second is a formal proof. By using the triangle inequality and our protective bubbles, we proved that having two limits is impossible. It would mean a number is smaller than itself, which we know is wrong. Finally is importance. The theorem is the foundation of calculus. It ensures that when we calculate a limit, we get one clear and stable answer that we can trust. In this class, we see that the math is about being exact. Knowing that a limit is unique gives us a strong starting point for everything else we study in analysis. And then, thank you for your time and for listening.